Hello, everyone. I'm Michael Foster. I'm a postdoctoral fellow at Macquarie University in experimental petrology. And in this presentation, I will show you the work I did with Kate Selway on the formation of magnetotelluric anomalies in the fore-arc of subduction zones. So many subduction zones are observed to have a strong magnetotelluric anomaly that sits just in front of the volcanic arc. So on the right-hand side image, we see that this anomaly, independent of the position of the trench, sits normally around 30 to 50 kilometers in front of the volcanic zone. And this is a really strong anomaly that is seen by its very low conductance or very low resistance in the magnetotelluric image. And a really good image is given at the subduction zones of the Cascades at the Mount Rainier transect. And here we see really good in image B from the study of McGarry et al. That was published in Nature, that this anomaly originates at the slab fore-arc border and then goes in front of the volcanic zone, rises into the crust, and then sits around 30 kilometers in front of the volcanic zone. And these authors interpret this anomaly as a pathway of melt movement from the melting zone in the mantle and then through the fore-arc in a clockwise rotation to the volcano. But the problem is, in our view, that the asthenosphere, where the melt originates, is mostly outside in the zone. So the zone mostly occurs in the cold mantle where normally no melts are found. So we asked us, when we zoom in, we see that subducted sediments can already start melting here at the intersect to 700 degrees, just in front of it, while arc magmas, they form at 1200 degrees or above, because from all subduction zones, there are also basaltic magmas known, and they have melting temperatures from at least 1200 degrees here. But the question is, what happens when we have sediment melts that are really cold and that then come in contact with the cold fore-arc mantle, that is where the temperature is too low to form basaltic melts or even andesitic melts. So for this purpose, we simulated the setting by using a natural sediment composition from the Mediterranean and put it in a reaction assemblage that consists of a sandwich of the sediment at the lower part of a capsule and dunite in the upper part of the capsule. And this sandwich then was processed into high pressure piston cylinder apparatus, where we simulated the condition inside Earth's mantle from around 3 GPa and at temperatures that are below 1000 degrees. And what we saw was really interesting. So we have here a reaction zone that developed between the sediment and the dunite. And this reaction zone got enriched in elements that were derived from the sediment melts. And so it enriched in aluminium, silica, and most pronounced here in potassium. And we see that all the potassium is now within a phlogopite-rich layer in the middle of the reaction zone, while the sediment below doesn't really show any potassium left, because everything moved into this reaction zone. And when we see these experiments in the relation to the global range of slab surface temperatures, we are of course at the hotter end, because the simulation with the experiments would take much long time at the colder end, but we are within the range of the subduction zone temperatures. And we see that the phlogopite-bearing, or this reaction zone that consists mainly of phlogopite and pyroxenite, that it really forms at the pressure temperature conditions that we have just in front of the volcanic zone in the subduction zones. And also that these phlogopite-pyroxenites, they're also stable, because phlogopite melting and phlogopite-pyroxenite melting occurs also at higher temperatures that are well above 1000 degrees, and it starts at 1100 degrees. And there are also natural examples that we have this fore-arc metasomatism, but we don't see it during normal volcanic arc magmatism, but there are examples where the magmatism moved into the Fore-arc and melted these metasomes, these phlogopite-bearing. And the first example is from Mexico, where we have like the Miocene volcanic front that not erupted medium potassium to high potassium lavas, common for volcanic arcs. But then there happened slab rollback in the Pleistocene, and this slab rollback led to the movement of heat from the convecting asthenosphere to this Fore-arc metasome, and suddenly these phlogopite-bearing are above the melting point and start melting, so we get oceanic to leucitites that erupt then in the Fore-arc of the volcanic front. And this is a nice example of this that confirms that we have these phlogopite-bearing present within the Fore-arc of subduction zones. Another example that is currently happening is at the junction of the Isobonian to the Mariana Arc. And the Mariana Arc moves out to the Pacific because of slab rollback. And at the junction towards the Isobonian Arc, we also have the slab rollback happening at the moment. And so we tap the metasomes there at the moment, and in this, it's called the alkalic volcanoprovince at the junction. We also have high potassium magmatism to oceanic magmas that erupt only here, while the Isobonian Arc in the north and the Mariana Arc in the south end are of normal arc magmatic composition. So for a short time, as this slab rollback occurs, these metasomes that formed during the subduction from metasomatism then melt. So, and then we thought, when we have these phlogopite-bearing, Kate Selway then modeled how they would look like in terms of the magnetotelluric anomaly in a forward modeling. So we put in at the model at the junction, we have at the intersection of the subducted slab to the Fore-arc mantle, we have the phlogopite-bearing, while above of the phlogopite-bearing, we still have a saline fluid that is rising to the surface. And we thought a saline fluid makes sense because the sediment melts, they can carry more water than the mica that forms during crystallization. So we have to exhaust a fluid that then rises to the surface. And that's how the anomaly then looks like. And the picture is really similar. So we have this column to the crust that is made up of fluids, and then the strong anomaly just at the slab surface where we have mica pyroxenites. So we don't think that we have this counterclockwise movement, but instead we have two pathways of a sediment melt that rises, but then gets stuck as it forms pyroxenites, and then the fluid emanates and goes to the surface, while only later, when the temperature is high enough, we have subduction zone, the normal melting, where then the mantle also melts and we get normal arc magmas. So in summary, we see that at really low pressure and temperature conditions, we have the normal serpentinites that are known from the Fore-arc of subduction zones. And just in front of the volcanic arc, temperatures are high enough to melt the sediments, and the sediment melts then rise and react with the cool Fore-arc mantle to form these mica-pyroxenites, and the fluid rises further to the surface, while only at the volcanic arc at the position of C, we have the arc magma generation, where also the asthenosphere melts and we get the normal basaltic to andesitic arc magmas. So I thank everyone for the attention, and our work is also available on open access journal Nature Communication if anyone wants to read further. So thank you very much.